In our next section here, we're going to be talking about some more along the lines with those internal and external and even like tangent angle properties. So way back at the beginning of this unit, when we talked about what makes something a secant versus a tangent, we talked about the difference between those kinds of lines. Now what I want to get into is when you start to have more than one of these types of lines drawn into your circle, what does that mean in terms of finding angle measurement? So we've talked already about the difference between a central angle and an inscribed angle. So now we're going to get into how do we start working with these tangents and secants that we've seen from time to time, and how do those angles inside of the picture start to work? So you can kind of see my first chart here has a couple of different scenarios that could happen where we have this first one talks about two secant lines, and when they intersect, it's outside of the circle. So right here is where those two secant lines crosses. You can see how that's on the exterior of the circle. When they cross on the inside of the circle, so like in this case here, again, we're still dealing with two secant lines because they go through the circle, hit the circle twice, but now they cross on the interior. That looks a little bit different than the first one. And then the third case is when you have it on the circle. So they happen to share a point. When both of those secants are drawn through the shape, they have one point in common. So we're going to be looking at these different scenarios and how you figure out how much maybe the angles are inside, like where those lines are crossing, or maybe if you're given the angle, how do you use that to help you find the measurement of the arcs that are on the edge of the circle? So we're going to kind of go case by case and kind of see some of these are going to be really similar to what we've done in the past, where we had to already deal with those inscribed or central angles, okay? And then we'll kind of get into the cases that we haven't maybe seen before. So I'm going to start with the case where when the secant lines are drawn, or maybe you have a tangent line and a secant line, because any of those three situations that I presented you with, they don't have to necessarily both be secants. One could be a tangent and one could be a secant. And so we're going to start with a case like the third one, where when they hit each other, it's on the circle, okay? So we're talking about this theorem that says if a tangent and a secant or a chord, it doesn't even have to be a secant line, intersect at a point on the circle, then the measure of each angle formed is half of the measure of its arc. And again, we're thinking about the intercepted arc. Where do the endpoints of my angle go? And what's the arc contained in between that? That's that intercepted arc that we talked about before in a previous section. So on this picture over here, this line where it says like B and it's kind of got these arrows going this way and this way, that's our tangent line, okay, because it hits the outside edge of the circle. This other one that has D on it, this one goes through the circle, so that's going to be our secant line. When they hit each other at that point B, that's on the circle, two angles are formed. We have angle 1 here, and we have angle 2 here. Okay, so we're talking about how would we figure that out? Well, you have to look at the arcs that they're intercepting. So if you look at the endpoints of 1, it goes from D to this point here. So we'd be talking about this entire arc that goes like all the way around. Whatever that arc would be, let's just say it's 300 degrees, okay? We would still do what we did in the last unit. We would cut it in half. Okay, so I'm just going to write, let's say this was 300. Then this here, this angle 1 would be half of that, so this angle would be 150. Okay, that's what we saw when we were dealing with the inscribed angles. Okay, that's no different. Now, same thing for 2. We would look at the arc that it inscribes. It goes from D, okay, this time going the opposite direction here to B. So if that first one was 300, that would have to leave this arc to be 60. And so the angle 2 would again be half of that, so 30. So very similar to what we've seen before in the past, just maybe drawn a little bit differently on our circle here. So let's do some examples. Now, like we saw in the past, they may give you numbers that they want you to find. They may start throwing in X's and Y's here today. So they can kind of start to change how they're going to represent what they want you to find. So for this first one, I want to figure out how much angle 1 would be. I would think about what we did in the last week. If you need to, trace over the angle that you're working with. Kind of outline the edges of the angle there. So you can see, okay, we're talking about this arc right here, which they're giving me is at 112. So what are we going to do with that 112 to find 1? Yeah, we're just going to cut it in half. So what is half of 112? Yeah, 56 degrees. So there's angle 1. Pretty cut and dry. But like we saw last week, are they all going to be like this? No. Sometimes they're going to give you maybe something else in the picture that isn't directly helpful to what you need. And you have to do a little bit more thinking or a little bit more work with the picture in order to get to where you want to be. Okay? So let's take a look at the next one. I want to find x and I want to find the measure of angle 1. Notice how x is on the outside of the circle. They're talking about an arc for x. And then angle 1, that's like what we just did before. So let's take a look at what they give you in the picture. This 78, I believe what they're trying to say here is that 78 is talking about this arc length of the circle. Okay? So anyone have an idea of what we could maybe do to start? You could find x, right? Because we know how many degrees are in a circle. 360. Okay, so to find x, let's just start by taking 360 minus the 78, which would be, good, 282. So that's this whole arc from this point all the way around the circle here. That's 282. What would we do then to find angle 1, which is this angle here? We would just take half of that, right? Because it's the intercepted arc, that 282. So to find angle 1, we're just going to take 282 divided by 2, and that leaves me with, good, 141. Very good. All right, why don't you guys take a look at this next one and just see what you can do with it by yourself. Okay, can someone tell me how they maybe started this problem? Yeah, go ahead. Okay, so you started with this angle that they're giving you here. I just want to make sure I understood what you said correctly. So we started with this, and so you knew that that hit this arc, right? Okay. Yeah, that's perfect. Now, be really careful with this one, okay? Because I think some of you might have maybe been trying to just divide by 2 because that's what we saw in the last couple of examples, right? But we talked about this, how sometimes they kind of get you into that habit of giving you the arc, dividing it by 2. Now they're switching it on you. They're giving you the angle. So remember, we want to double the angle to get to the arc. So what they said was to find y, they took the 118 times 2, they doubled it. And so y came out to be 236. That's great. Now that would be this whole arc that I have kind of colored over in yellow. So someone else out there then, maybe if you got to this point or if you didn't, maybe at this point now you would know how to find x. What would we need to do? Yeah, since x is just talking about the remainder of the circle here, using our prior knowledge on circles, we know that there's 360 degrees total. So take away that 236 and we get left with, good, 124. And there's your x. Very nice. All right. Do we have any questions on those first couple of examples here today? Okay, so like I said, those are pretty similar to what we were doing when we talked about inscribed angles. Not identical, but kind of the same idea. right? The relationship between the arc and the angle that we're working with, since they're inscribed because the vertex is on the side of the circle, really no different than what we were doing, okay, as far as the math goes. And so let's also review what we've talked about before as well. So we kind of went over, the inscribed angle idea. We're seeing that happen still. What did we talk about last week about central angles and their arc? They're equal, right? So these two measurements on my circle here are going to be the same. So I'm going to say, here it goes. We already know central angles are equal to that intercepted arc. We know this. Okay, so the x and the x are the same. And then what we just talked about is those inscribed angles. When it's on the edge of the circle, how they're not the same anymore, but there's still that relationship of the angle is going to be half the measurement of the arc that it's intercepting, okay? When we look at this situation, this is going back up above to the very top of your page there when we talked about those three scenarios. We've dealt with the last one. Now we're kind of working our way backwards on the chart. This time I have these two secants and they're intersecting on the inside of the circle. Okay, looking at this picture right here and maybe primarily at those angles that they have kind of with the arcs and shaded in a little bit, what do you guys know about those angles by just looking at the picture? You know they're the same because what kind of angles are these? Yeah, these are vertical angles, okay? So vertical angles are congruent. We've talked about that a long time ago. Okay, we talked about congruent angles and all the different angle pairs, right? And vertical angles shows up and it's been kind of showing up sporadically throughout this unit. So these two angles here are always congruent to each other. Do you think, just by looking at the picture, you don't have any numbers, so you just kind of have to use your best judgment. Do you think that the arcs that they're intercepting, so this kind of the left side is intercepting this, and the right side is intercepting this? Do you think that those are the same? You think they look a little different? Maybe a little bit different, right? The one on the left, to me anyway, seems to maybe be a little bit more of an arc than the other one does on the circle. So I don't think we can say that just because you have vertical angles that they would be the same. It's maybe even more apparent on this side. Like if we're looking at the other half here, I think that this arc is much smaller than this one. Would you agree? So I don't think we can say that they're equal. So let's turn our page and figure out how do we deal with this situation. So we've got our next theorem for the day here. It says, if two chords intersect in the interior of a circle, then the measures of each angle is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. Okay, that's a lot of words, right? There's a lot of stuff that's being said there. So let's kind of break this down into what we were just looking at. We see a couple of different pairs of vertical angles in our picture. So what this rule is saying is if you can see those vertical angles and then you can match those angles up with the arcs that they're intercepting. So kind of think about what I was doing on that last problem as far as like tracing the arcs. I kind of did that in like the red and the blue. If you can figure out how much those arc measurements are, we can add the two arcs together. This is actually missing the arc symbol. So if you want to add that into your rule here, those should have those symbols. At least mine's missing it. I don't know if your guys's are. But if we can add the two arcs together, and if we can cut that in half, that is going to give me the measurement of both of those angles. Because they're vertical, their measurement should be the same. So they're naming them AEB, that's this side of the vertical angle, and then CED is the other side. Remember, when we're naming vertical angles, we probably need to use all the letters because we can't just say angle E because there's actually 4 angles that have E as a vertex. So we want to be a little bit more precise when we're naming them. But so if I know how much these two arcs kind of on the outside of those vertical angles are, I would add those together, cut it in half, and that would tell me how much the angles are, the vertical angles. Now I could do the same thing for the other pair of vertical angles in that picture. Okay, those other pairs that are kind of going up and down from each other, I could also figure out how much those are by doing the same thing with their respective arcs. Okay, so let's do some examples using this theorem, starting with this one. So this is basically just using that rule from up above. X is one of these angles that's kind of on the interior here. I would say this is vertical to this angle here. I've got the two arcs that are across from those, so 55 and 107. So all I need to do to find X is take half of 55 plus the 107. What is that going to be? Good, 81 degrees. Okay. All right, now let's take a look at number 2. Is the second one the exact same as the first one here? It's close, right? We're still kind of working with vertical angles, kind of almost looks similar to how the other one is set up as far as maybe what you're trying to find. But the X is in a different location. It's not inside with the angle, right? Okay, so let's think about how we set up the last one and how that's maybe going to relate to this one. Where was X at on the first example? It was inside by the, like where those secants cross, okay? What is there on my second picture this time? The 71, right? So instead of starting with X like I did on the first one, I should probably start with that 71. So let's begin by putting 71 down, and then we're going to set it equal to. Now I know in my kind of formula from up above that I have a half, and then in here I have my two arc measurements that I'm adding together. So back on the example 1, that was the 55 and the 107. What does it look like for this one? 92 and the X, right? So all I did there was kind of look at the first setup, and I modeled this problem off of that. Now you'll notice how my variable is in a different spot, okay? And I don't have X at the beginning. I have 71 at the beginning. So we're going to have to maybe do a little bit more thinking here to get this solved for X. I see that 1/2, and I would really like to get rid of it if I can. Could I distribute it to the 91 and to the X? Yes, but it would be great if we could just get rid of it, right? If we could get rid of that fraction, it's going to make things a lot easier, I think. How could I get rid of that 1/2? I know some of you want to do divide by a half, right? But I think dividing a fraction by fraction can be a little confusing at times. Is there another way besides dividing by a half that I could get rid of it? Take it times 2. If I take this side times 2 and this side times 2, that'll get those halves to cancel because they're reciprocals. And then I'm just multiplying over here, 2 times 71, which would be 142. And then I just have over here 92 plus X. Okay, great. What would you guys do next? Subtract the 92 and you get 50. Very good. Great job. Okay, so see how that one was a little bit different? You might have that and you got to work kind of backwards. So it is possible that they might do something like that as well. All right, let's go on to the third one here. All right, take a look at this picture and maybe just kind of compare to the other two. What's different on this one? Okay, so you're noticing that the arcs that they give you aren't necessarily connected to the X, right? Okay, so maybe because of this one, I do ultimately need to find X, but I think it would be helpful if I could figure out how much maybe this half or this half of the angle is, those vertical angles. Because in the same idea of vertical angles, there's also what other angle pair present here. The x and this angle here together make a what? They make a linear pair, okay? So if I could somehow maybe find the other half, then I could use the fact that I know it's a linear pair to help me get to x. Okay, so how could I maybe figure out how much those other angles that are unmarked, maybe let's call this a y. How could I solve for y? Yeah, go ahead, tell me how you would set it up. Good, you're going to take a half times 82 plus the 146. Great. So what did you get, or what would you get? 114? Okay, great. So that's y. Now, I didn't really need that, right? That wasn't what they were asking for, but I do need it to maybe help me find my x. So remember we said that the y that I just found and the x make a linear pair. What do linear pairs do? They add up to 180. So shouldn't we just be able to take 180 minus 114 now? And we get, good, 66. Very good. And that's really what I wanted, okay, from the picture. Good. Okay, so kind of a little bit different than what we've done in the past where we're working with multiple pieces there. We needed to know the measurements of both arcs before we could do anything, or we needed to know the measurement of one arc and maybe a vertical angle in order to do that. So that's a little bit different than what we saw in the past. Okay, we've got one more case that we need to get into. So we've talked about when they intersect on the circle. Now we've just covered when they intersect inside the circle. Now let's go over to the case where they intersect outside of the circle. Okay. And I had one example up in the chart on the previous page, but this kind of breaks it down even further, where you could have multiple cases where this happens. You could have it being two secant lines that do end up crossing through the circle twice that intersect on the outside of the circle. You could have where one of the lines is a secant and one of them is a tangent, or you could have a situation where you have two tangents and they're both on the outside. Okay, so all three of those cases are acting the same way in that they intersect outside of the circle, but they consist of a couple of different types of lines. When we're trying to do this one, we are still going to be working with arc measurements and kind of doing something with them, but it's going to look a little different than what we did in the past. So let's look at this next theorem. It says if a tangent and a secant, or two tangents or two secants, so if any of those three cases from up above occur, and they're hitting each other on the outside of a circle, the measure of the angle that's formed, so again, think about those vertical angles, is 1/2 the difference of the measures of the intercepted arcs. So on my picture here, I'm just going to zoom in. What they are saying is if I wanted to figure out how much this angle was here, kind of where they have that arc and kind of shaded in, I would need to know how much is this arc from A to B, and I would need to know how much this arc from C to D is. I would then take the larger arc, AB, and I would subtract the smaller one, CD. So take like that farther away arc minus the one closer to the angle, and then you're still going to take half of that. So you can multiply like a half like we did on the last couple, or you can think about it as dividing by 2 if that's easier. So for example, if this arc here was 100 degrees, and this one here is 20 degrees, what this would look like to find this angle here is we would take 100 minus 20, and we would divide by 2. Okay, and that would come out to be 40. So that angle in there by E would be 40 degrees. Okay, so let's do some examples here. Last couple that we have for our day. So find X here. This is very much like what we just talked about. It's fairly cut and dry. So tell me how we would set this up using what we just talked about. Good, 93 is the bigger one, minus 29, yep, and then good, divide by 2. And what do you get there? Good, 32. Okay, take a look at the second one. How does it compare to the one that we just did? It's pretty close, right? It's just your x is in a different spot. Just like what we saw up above when we did the last case, they kind of moved the pieces around a little bit. So let's think about how we would set this up. Use your first setup to kind of model if you need to. When we put x that was out here, what are we going to put in that place over here on this one? Yeah, the 59. Good. What are the arcs that we're going to subtract? Yeah, 168 minus the x, and it's all over 2. Okay, why don't you guys take a second and see if you can solve this one on your own. Someone want to tell me what they did? Okay, I heard multiply by 2 first. That gets rid of that. It'd be the same thing if we were doing it times a half, just like we did on the example from up above. Okay, so then you had 118 equals 168 minus x. You subtracted 168, so 118 minus 168 is negative 50, and then this equals a negative x. We can't leave an x negative like that, so what's the last thing we need to do? Yeah, just switch its sign, right? We just get rid of the negative 1, but that also affects the number, so x is actually equal to, yeah, just 50. Good. Make sure you don't leave it negative. Okay, when you're doing really any of these problems today, if you're filling in for an angle or an arc, probably shouldn't be negative. Okay, we haven't talked about measuring circles in negative degrees or angles in negative degrees in this unit, so we probably don't want to have negative numbers. Now, if you're talking about like a variable that would maybe get plugged into an expression, it might be okay to have a negative, but it would not make much sense to leave that as negative 50 degrees. Okay? All right. We got one last one here. We got to think a little bit. I need to solve for x and I need to solve for y. Anyone have an idea on how to do either? What do you see? Tell me what you're thinking. Okay, you want to solve for y? Okay, tell me how you're going to do that. Okay, so you saw a full circle, 360, and these two numbers that they give you, 93 and 183, those are those arcs, and y is just the remaining piece. That's why you're setting it up like that? Okay, great job. And what does y come out to be? Good, 84. So there's your y. So that would go right here. Now, can we set up x? Yeah? Should just be like what we talked about from the theorem, right? Because now we've got both of those arcs. So to find x, we should just be able to take 183 and then do what? Subtract 84 and divide by 2. Good. Okay, and what do you get? Yeah, don't let the decimal make you think that you did it wrong. Yep. Okay, 49 and a half. Yeah. I know sometimes when we get decimals that it makes us think we did something wrong because we haven't had a decimal yet. But it is okay to sometimes have that happen. Okay. Any questions on that last one or those last couple of examples at all? Okay, I know we went over a lot of different scenarios today. So I'm going to get you guys a worksheet for you to kind of practice each one. And hopefully as you continue to practice, it'll start to maybe make a little bit more sense. But when you're starting these problems, the one thing that I would really suggest that you do is look at how they're intersecting and where they're intersecting at. Is it on the circle, in the circle, or on the outside of the circle? Because then that'll kind of help you narrow down which situation should I be using. Okay, so make sure as you're kind of practicing today that you're using the appropriate setup when you're trying to solve for something. Okay, all right, let's get that out to you guys, and you have the rest of class time to be working on that.